Hello, and today we're going through applications of calculus for further maths, A-level. Let's get started. So first, let's start with the Maclaurin series. So the Maclaurin series is an expansion of a function which expands into a function like this. So you have a series where you add different parts of the sequence. So the formula for the Maclaurin series is f of x. You can expand to f of 0 and then you differentiate it, so you get f dash of 0 times x, and you differentiate twice and divide by 2 factorial and then multiply by x squared, and you keep on going, keep on differentiating the top and keep on dividing by increasing numbers of factorial. So for the next term you would have f differentiated 3 times, the function differentiated 3 times, and substitute 0 in, and your next one would be, so if this one's 2, this one would be 3, so you could divide by 3 factorial, and you multiply by a power of x, so here's x squared, so the next one would be x cubed, for example. And yeah, I wrote it here as f to the n, which just means that you have differentiated n times the function f of x, and you substitute 0 into the function each part of the series. And in factorial is, remember, just n times n minus 1, and you keep going down, multiplying each one until you reach 1. So even for this one, before, you see us divided by 2 factorial, this is the same as 1 factorial, because 1 factorial is just 1 times itself, so you just divide by 1, which is the same as this. So in theory, it actually is increasing numbers of factorial. And it's also worth mentioning that if this one was 0 factorial is equal to 1. So this would just be f of 0 as well. And because the power would be 1 less than this one, so x to the power 0 is just 1, so you just multiply by 1. So now let's move on to a question. So the question asks, find the first 4 terms in the Maclaurin series of the expansion of cos x. So I wrote out the expansion of the Maclaurin series from the formula that we had before, and because we want the first 4 terms, I've done the first 4 terms here until x cubed. And so our first step would be to find what f of x, f dash of x, and f dash dash of x, and the third derivative is. So I've written out each one of them. So cos, when you differentiate cos, you'll get minus sine, and when you differentiate minus sine, you'll get minus cos. So you keep differentiating, and then minus cos, when you differentiate, you'll get sine. So you keep differentiating as you go down. So you got cos, minus sine, minus cos, sine. And because we substitute 0 in the formula here, as you can see, we can just substitute 0 into the equation. So f of 0, f of 0, f of 0, f of 0. When we substitute 0 in cos, you get 1. When you substitute in sine, you'll get 0. So for this first derivative and the third derivative, you'll get 0 because they're both sines. And because there's a cos here as well, you'll just do, because when you substitute 0 in cos, you'll get 1, and because there's a minus, you'll get minus 1. So now we substitute all our values for f of 0, f dash of 0, f dash dash of 0, and f, so the third derivative of f substituting 0. If we substitute into the equation, we'll get something like this. And because the 0, we can just cancel it out, so we'll just be left with 1 minus a half x squared, which is the same as small angle approximations, if you remember from A-level math. However, because we've lost 2 of the terms, and now the question still asks for 4 terms, we've only got to have 2 terms, so we need to find 2 more terms because we have 2 of them already. So here we'll just carry on differentiating over here. So we'll go to the 4th differentiation, which is just differentiation of sine. We differentiate to get cos, and we do that again for the 5th and the 6th just to make sure. And when we substitute cos 0 into the cos, we're just going to get 1. So cos 0 is 1, minus sine 0 is going to be 0, and minus cos 0 is minus 1. And here we are sure to get 2 more terms because the 0 is probably going to cancel out again. So here we have the same equation from before, but we just extended it to higher numbers of a series. So it's just the same equation that we have here, but we just extended it further. So here, remember we got this from before, the small angular approximation basically from this part over here. And then for the rest, basically what we've substituted in 0 for all of our values here, here, and here, and we substitute them in, and we're going to get this, which we can get rid of the 0, as we said before, and we're left with 2 extra terms, which we can just add them on to the Maclaurin series that we found before. And now we finally get 4 terms of the cos x. So now let's move on to Maclaurin series for common functions. So as you saw before, the equation we saw before over here, this is a Maclaurin series equation for all types of functions. And because if just to skip the step of differentiating multiple times of the function to find the coefficients of each of f of x, for example, we can just memorize the Maclaurin series for these common functions. So for example, e of x will just have 1 plus x squared over 2 factorial, and if we carry on, we'll get x cubed over 3 factorial, and then x to the power of n over n factorial for increasing terms. And then for this format, ln of 1 plus x, you'll get, starting off with x instead of 1, so you get x minus x squared over 2 plus x cubed over 3. Remember, these are not factorial, as you can see. And then you keep adding on, and then you get minus plus minus plus, so technically plus minus plus minus, and then this will alternate the whole time. So you have minus 1 to the power of n plus 1. So here's when your n plus 1 is even, you'll get positive 1, and when it's odd, you'll get minus 1. So this shows the alternation between minus and positive, and you either, and then you do the x to the power of n over n, and not factorial. And for sine, same thing. So sine will just be x minus, and then you go to an odd, so you get x cubed 3 over 3 factorial plus x to the power of 5 over 5 factorial. And then remember the plus minus over here, and here is slightly different because instead of n plus 1, you have the power of n, which represents this plus minus oscillation. And because to show that the powers and the factorials are all odd numbers, you just use 2n plus 1, 2n plus 1. And for cos, you would use even numbers, so instead of 2n plus 1, you would do the 2n, as you can see here. So you do 1 minus x to the power of 2 over 2 factorial, x to the power of 4, 4 factorial, minus, plus minus, so you do this same thing here. And the x to the 2n, so an even number, over 2n factorial, and which shows another even number, or factorial of an even number. And then if you have 1 plus x to the power of a number r, any number or any integer r, you can do 1 plus r times x, and then r times r minus 1 over 2 factorial. So you keep adding on, and you'll do r times r minus 1, multiply, keep multiplying until you get r minus n plus 1. So you keep reducing the number, and minus n plus 1. And then you divide this all by n factorial, so n is just the number of the series. So like this would be 0, so this would be 0, 1, 2, and then you keep going, so this one will be 3, and then multiply it by x to the power of n. So here was 2, the next one will be 3, etc. So now let's move on to a question. And here it asks to find the first 5 terms of the Maclaurin series of e to the x cubed. So as we saw before, that e to the x has a known binomial Maclaurin expansion, Maclaurin series, as we see up here. And if we substitute our x cubed into the x of the Maclaurin series, so we'll make a new Maclaurin series of a instead of x, so like this, which is basically the same as this, but instead of x we have a. So 1 plus a squared over 2 factorial, a cubed over 3 factorial, a to the power of 4 over 4 factorial. And because we found the first 5 terms, this is enough. And if we substitute our a as x cubed, we'll just use the same formula and plug in x cubed into each one of them. And in the end, we're going to get this as our Maclaurin expansion. So we'll get 1 plus x cubed plus x to the 6 over 2, x to the 9 over 6, and x to the 12 over 24. And as you can see, 2 is 2 factorial, 6 is 3 factorial, and 24 is 4 factorial. So now let's move on to integrals where the range goes to infinity. So these are called improper integrals. So this is when your integration range goes to infinity. So this is an improper integral. And when it comes to this, just for the method marks in the exam, they would require you to turn this into another format where you have limit of b goes to infinity, and you do between b and a if you do from infinity to a, like here. So you'll have to add this limit at the end, so you have two values like this for the integration. So now let's move on to a question, so we can practice this. So for example, if we're trying to find the integral of infinity, from infinity to 0 of this, how would we do this? So first step would be to get rid of this infinity and substitute a b, for example, in there, and then say that our limit is when b reaches infinity. And this, from here on, we'll just follow basic integration from A-level maths. So here we can split it up into two integrals because you have the minus in between. So you can do the limit of b goes to infinity, b and 0, and then you substitute each fraction separately. So you integrate it separately. And because in this one you have 6, you can actually take out, so because you can take out the 2, so you take out the 2, because you want to leave it in this format. If you remember from A-level physics, A-level maths, if you have this format where you have the differentiation of a function on top divided by the function itself at the bottom, you can integrate this to get an ln form pretty easily. And because you want this for this one, you would want to leave 3 at the top because the differentiation of 3x plus 2 is 3. So you would want to leave 3 at the top. So you can take out 2, like here, and leave 3. So that this is the differentiation of this. And if you look at the other function, the 2x and x squared plus 5, if you integrate differentiate x squared plus 5, you're going to get 2x. So this is already left in a really nice form that we can turn into an ln when we integrate it. So once we integrate this and leave the limits out, we're going to get the ln of the function at the bottom inside of the brackets minus, and then because we had the minus 2 left out, so we can have the minus 2 out. We don't need to integrate that anymore. And then we'll do the ln of the function at the bottom of the brackets, which was the 3x plus 2. And remember to leave it in the modulus form. And we still need to leave the limit b goes to infinity and between b and 0. And because of log laws, because we have a function, so we have a function take away a multiple of ln of another function, we can just do, when we do take away, we can leave it in terms of a fraction inside of the ln, and because we have a multiple outside, we can actually raise to the power of whatever's in the inside. So we can have the g of x to the power of an a, like this. And because we had multiple of 2 and we had a takeaway in between, we can just do the first function divided by the second function to the power of 2, as you can see from here. So the 2 becomes the power here, and then you'll do x squared plus 5 divided by this to the power of 2 because it's multiplied by the power of 2. And once you do this, you can plug in the limits and take away each one. Make sure to still keep the limit of b goes to infinity. And then you can, once you substitute the limits, you'll realize that this one has no b, so you can actually take out of the limit. So the limit is left there, and then you get 5 over 4 limit, and then only the part that has b in it. And then once you finally plug in what infinity is in the b, so in this case, you can go to your calculator and just plug in a really large number for b. So I did, for example, 1 times 10 to the 20 in my calculator, and then in the end, I got something that approached 1 over 9. So I'm assuming that as b reaches infinity, this value would become ln 1 over 9. So we're left with ln 1 over 9 minus ln of 5 over 4. And now all we have to do is just join this together into one ln, just to leave it nicely. So log laws, we do the division, remember from before, and we will be left with ln 1 over 9 divided by 5 over 4. And then you can do the keep, change, flip from GCSE maths, and then flip the 5 over 4 to become 4 over 5, multiply them, and we're going to get an ln of 4 over 45. And this is the answer to the improper integral that we had over here. Now let's move on to integrals where the range passes at a point which the function is undefined. So this is another type of improper integral, but instead of going to infinity, we're going to a point, like say k here, where the function itself just goes to infinity in the y-axis. So either positive or negative infinity. And as you can see here, say k is undefined when x equals k, the function is undefined. If we want to integrate between k and a, we would have to do the limit as well, but b goes towards the k, and substitute b into here. And again, if you have your k in your lower bound, so for example you have between b and k, you would have to add another value here, so a goes to k, and then substitute the a here, and do your limits. And if you have a in between 2 points, but say those 2 points are a and b here, and in between them there is a point that goes all the way up to infinity, so an undefined point. So in this case, you want to apply your limits, but you actually want to do into another constant. So you say your c approaches k, so your limit c approaches k, and you want to go from a to c, and then from your c, so say from a to your k, which you substituted as c because c approaches k, so from your a to your c, and then go from c all the way to your b. So you have to split it up into 2 and then add them together, so you have 2 limits. And this is mostly for working out in your exams, and just to understand that you can't really just integrate it straight away in your calculator, for example, when you're doing these kind of integrations, because it goes up to infinity. So now let's go on to a question where we have find the integral between 3 and 0, and then for of this function basically here. And we realize that if we that when we do 1 over 0, basically you'll get an undefined, because when you divide by 0 you're going to get infinity. So we realize that this happens when you have your x value as 2, because 2 take away 2 is just going to be 0. You can have 1 over 0 basically, and this is undefined. And we realize that 2 where our function is undefined is between 3 and 0. So what we want to do is use an improper integral on the functions that we used before, so this one here, because in between 3 and 0. So our first step would be to, again, separate it out into 2 integrals like this, and apply our limits. So in this case we had 3 and 0, we can just split it up in between 3 and 2 and 0, because 2 is the point where it's undefined. And because this is a improper integral in itself, the 2 is going to have to be, like, we're going to have to apply the limit. So limit of a approaches 2, and you substitute your a instead of 2 into the function. And now all we have to do is just integrate this in the inside, and this is basically a function to the power of something else, and we can use integration by substitution. If we make our u the function of the inside, so x minus 2, or du over dx is just going to be 1, so you get rid of the minus 2 and you'll be left with the 1 where you differentiate from the x. And then if you rearrange this equation, so multiply by dx on both sides, you're going to get du is equal to dx. And because of integration by substitution, now because your du is equal to dx, you can substitute the dx as du and your function here as u to the power of minus 1 over 3 as we had before. And then when we integrate this, it is pretty easy to integrate. You increase the power by 1, so you get 2 over 3, and then you multiply by, or divide by the new power, so you do divide by 2 over 3, which is the same as multiplying by 3 over 2. And now you can substitute your u back, which was the old value that we had, which was x minus 2, into the equation, and this will be your integration, basically. And This will be our integration for the lower limit, so between 3 and 2, or 3 and a, as we made our a 2 because it's undefined at 2. So now we know, because our integration will lead up to this, because we found this using integration by substitution, we can just apply our limits, the 3 and the a, and we'll have 3 over 2, 3 minus 2, we can substitute the 3 as the upper limit, and then substitute our a as the lower limit, and we don't need to really apply the limit at in the 3 because there's no a in the equation here. So then we're going to get 3 over 2 minus the limit of a goes to 2 and this function here. And if we substitute 2 here, we're going to get 2 minus 2, which is 0. And 0 to the power of anything is just going to be 0. Multiply another thing, it's just going to be 0. So we're going to be left with 3 over 2 minus 0, which is just 3 over 2, for the integration between 3 and 2 of this function. And now, our next step would be, because we found the between 3 and 2, we're just going to have to find between 2 and 0. So if we integrate between 2 and 0, we're going to do the limit again, and we're going to substitute our 2 as a as before, but it's going to be our upper limit now. And if we integrate this, remember we know from before our integration by substitution previously from over here, we substitute the integration and then our limits here. And if we substitute our limits, we're going to get something like this, where we apply our limit only to the outside and our limit and no limit to this one because there's no a here. So we're going to get our limit of a approaches 0, approaches 2 of this function minus the cube root of 4, which is what we found from here, basically. And if we substitute a as 2, 2 minus 2 is again 0, so we're going to get a 0 for the whole thing. So we're going to get 0 minus the cube root of 4, and this is going to be our integration for our other thing that we found. So our other point that we found between 2 and 0, because we did between 3 and 2 for the first part, and now we did between 2 and 0 for the second part. And for 3 and 2, in between our 3 and 2, our integration we found that was 3 over 2, and for the 2 and the 0, we found that it was minus the cube root of 4. And now, because we have to add them together, if we add them together in the formula, we're just going to get 3 over 2, add the negative of this, so you just take away the cube root of 4. So the integration that we found from before is equal to 3 over 2 minus the cube root of 4, which is our answer to the question. I hope that makes sense. So now let's move on to simple volumes of revolution. So this is the basics for volumes of revolution. So this is the beginnings. And basically you can have a function which looks something like this, like a curve like this, just this top part. Look at the top part. And you can actually, if you spin this function around the x-axis, you're going to get a volume of revolution like this. And you're going to have a whole volume because it's going to be a 3D thing, like it's going to have a volume. So to find this volume between 2 points A and B, the formula would be the volume is equal to pi times the integral between B and A of your function, which you can substitute here as y, because you have y is equal to something in terms of x, and then you square this function and differentiate it in terms of the x. And this is when it's rotated at 360 degrees. However, now if you have another function like this, for example, and you want to rotate it instead of the x-axis now, you want to rotate it around the y-axis between A and B. To find this volume of revolution when you rotate it about the y-axis, you're going to get between B and A times it by pi again, but instead of the y squared, so you have a function of x in terms of y, you substitute into here, and then you square that, and then differentiate your function in terms of y, basically. And we're going to do some questions just to see how it is. So let's move on to questions. So say we have a curve that looks something like this. So y is equal to 1 over x to the power 4, and this is rotated 360 degrees about the y-axis. And now we have to find the volume of revolution between y equals 10 and y equals 20. So as we said before, if we rotate it around the y-axis, we're going to get between, we're going to get this formula here. and we will have it in terms of x in terms of y, we substitute in here, and we differentiate in terms of y. So our formula will look something like this. And because it's between the 2 points of 20 and 10, we'll substitute our limits into the equation here. And because, remember, we have a function of y in terms of x, and we want an equation of x in terms of y. So what do? We rearrange the whole equation to get x the subject. So we have y is equal to 1 over x to the power of 4. Rearrange this, multiply by y, by x to the power of 4 on both sides, you get this. And now divide by y, you'll get this. And then, as you can see, you'll be left with x on one side once you do the fourth root of y here. And once you have this, so you have x in terms of y, you can substitute your new x, as we said before. So this is our x. X in terms of y, we substitute in here. And now we have an equation, and we can differentiate it nicely in terms of dy. And because we square it, if we do the fourth root squared, we're going to get just the normal square root. And remember, we multiply by pi, the limits are 20 and 10, as we said in the question. And this 1 over the square root is the same as the power of the minus a half. And this is very easy to integrate. You just increase the power by 1, so you'll get a half. So minus a half plus 1 is a half. And divide it by the new power. So divided by a half is the same as multiplying by 2. So you'll get this, and now all you have to do is plug in your limits. So substitute in 20, substitute in 10. So you'll substitute in your 20 here into this function here. So you have 2 times 20 to the power of half minus your 2 times 20, 2 times 10 to the power of a half, which is basically square rooting. And remember to multiply this whole thing by pi, and you'll get an answer of 8.23. And a few more decimals after, but I've just rounded it to this, which is good enough for the question. So now let's move on to volumes of revolution between two curves. So in the case before, we only had one curve, where you just have one curve, you rotate it in between the x-axis or the y-axis. And in this case, we'll keep it simple for further maths A-level further maths, where you only have to rotate it around the x-axis when you have two curves. So basically the formula is, if you have two curves and you're trying to find the volume in between them once you do a volume of revolution, so this volume here that I've highlighted, your equation will just be the volume is equal to pi times the two limits, so your a and b. And then inside the integral, you would have your f of x, which is the outer function, squared, take away your inner function squared, and then you integrate this whole thing together. So now let's move on to a question so we can see how this works. So in this case, it's asking find the volume of revolution enclosed between y is equal to x squared plus 4 and y is equal to 4x plus 2. So in this case, we would have, if we draw it out, so using a graphical calculator, which you're allowed in a level further maths, what you can do is actually look at the graphs, and you'll see that the y is equal to x plus 4 will look something like this. And even if you don't have a graphical calculator, you can actually kind of visualize this pretty easily, because you know this would be a quadratic because it's to the power of 2, and this would be a straight line because it's basically y is equal to mx plus c. And as you can see, there is a point of intersection, and there's a point of intersection between the 2 points, between where they intersect, and there's a area in between, which if you were to rotate it around, you could get a volume of revolution. So if we write out the formula from before, again, for volumes of revolution, remember our f of x is going to be our outer function. As we said before, f of x is our outer function, and your g of x is your inner function. So if we look at the graph, our outer function is going to be our 4x plus 2, as you can see here, and your inner function is going to be the quadratic x squared plus 4. So you can substitute your f of x as x plus 4x plus 2, and your g of x as x squared plus 4. And all that's left to do is to find our b and our a. So to do this, because we're finding the volume enclosed by the two, we have to find the two intersection points to find the area enclosed, so the two limits that enclose the the volume of revolution. So to do this, we basically equate both of the functions. So we make y equal to both of them. So you have 4x plus 2 is equal to the other function. So you equate the y's, and here you'll get a quadratic, which is easy to solve. Here I just completed the square, and once you complete the square, you'll get x minus 2 squared minus 4, which is just the 2 squared, and then you have the plus 2 left over from the 4, and then you can rearrange this because it's equal to 0. You have the 2 on the outside, x minus 2 squared. When you square root, you get the plus minus, and you have x minus 2 left on the other side, and then you'll get 2 plus minus root 2 is equal to x. And you can also use the quadratic formula for this, or even a calculator to solve this. And this will give us two roots, the 2 minus root 2, which would be the lower one, and the 2 plus root 2. So these are the 2 points of intersection here and here. And now we know everything that we can plug into the formula. Let's just solve it. So here we have everything plugged in. So this is our f of x, our g of x, and our b's and our a's. And we know that this one will be bigger than this one because when you add two positive values together, it's going to be larger than subtracting them. So this will be our upper and this will be our lower. And all we have to do is just expand this out, which I did using this. So 4x times 4x is just 16x squared. 2 times 4x is just 8x. 4x times 2 is 8x, and then 2 times 2 is 4. And I got this expression from multiplying out the 4x plus 2 all squared. And I did the same for the x squared plus 4, and then you get a quartic, which is 4x, and then I just added them up, 8 plus 8x squared, x to the power 4 plus 8x squared plus 16, and then you'll get an expression like this. If you join all the like terms together by taking away the first one to the second one, you'll get something like this. And then this is just easy steps, just multiplying out the squares and then collecting like terms, and then all that's left is the integration, which you do for each of one of them. You increase the power by 1, so 4 becomes 5, and divide by the new power, so divide by 5, so basically multiply by 1 over 5. And here 2 becomes 3, divide by 3, 8 over 3, and then 1 to x to the power of 1, and then becomes x to the power of 2, and then 16 divided by 2 is 8, so we leave 8 there. And here we don't really have to do anything but just add an x to the constant here. And now we can apply our limits. And remember to keep the pi on the outside as well. So once we apply our limits, we just substitute the x plus 2 as the upper limit and the x minus 2 as the bottom limit. And we'll get a final answer of 217.997, where I've rounded it, but it keeps going. This is enough accuracy for what we need. So now let's move on to volumes of revolution using parametric equations. So when you have parametric equations, you can also do volumes of revolution. Remember that a parametric equation is basically like y is in terms of t and x is also in terms of t, but they both represent, like these two equations will both represent one curve, like this, for example. And you can also rotate this about the x-axis and the y-axis. And when you do volumes of revolution for the x-axis and y-axis, all you have to do, because you're going to have your y in terms of t and your x in terms of t, or like theta or whatever, you would do between your t, your upper t and your lower t, whatever this part represents your t and whatever this part represents your t. So t represents either the initial part or the end part. And for the end part, we can call that tb and ta. And we'll do the integration between these 2 points, which would be our t, first and last t's. So when you have a parametric equation of, say, pi of integration of tb and ta, we would have a function of y in terms of t, or a third variable, which could also be theta, by the way, but I'm just using t for example. So you substitute our y in terms of t, so we'll have a function of t in here, and we square it, and then we would have your x in terms of t. If you differentiate that and multiply it by the y in terms of t squared, and then integrate the whole function, you can find the volume of revolution if you rotate around the x-axis 360 degrees. And if you do around the y-axis, you would just do the opposite. So you'll do your x in terms of t squared multiplied by the differentiation of this in terms of t. So you do dy over dt multiplied by your x in terms of t squared, and then integrate the whole thing there. And as you can see, you can memorize this pretty easily because this is the same as the previous equations that we saw here. So y squared dx and x squared dy. And if we look at our new equations, we've got the dt's can cancel out because this is a thing over dt multiplied by dt. You can basically cancel these out, and you got y squared dx and x squared dy because your dt's could cancel out. But we need the dt's for our parametric equations, so we leave them there. And that's a good way to just memorize the equations basically. So now let's move on to a question where it says there's a volume of revolution rotate about the x-axis enclosed by, so find the volume of revolution rotated about the x-axis enclosed by the parametric equations of x is equal to cos t and y is equal to sine t. So if you have a graphical calculator, you can actually show this on a graph. So you have y and x, and your parametric equations will show something like this in your calculator. And because we're trying to find the volume enclosed by this whole graph, so we would have to find these two endpoints because we're trying to find the area in between the whole thing. So because we know this looks like this in a graphical calculator, we can also check on the graphical calculator that this is -1 and this is 1. So we know that our endpoints are going to be -1, 0, because the y is 0 at that point, at this point here, and 1 and 0 because our y is also 0 at here, this endpoint here. So it's between -1 and 1. And because our x is equal to cos t, and we know that our initial point would be -1 and our final point will be 1 for our x, so it must be also be the same for cos t. We can just rearrange this equation to do the cos inverse of these two, and we find that our t values are pi and 0. So we can use our limits of the function, as we said before, between ta and tb. Our ta and tb would be 0 and pi. And we can test this out by substituting into the y equation to see if they actually intersect. So if we substitute sine 2 pi, because we multiply by 2t, so 2 pi in this case, we're going to get 0, and sine 2 times 0 is also 0. So we know that these are actually the intersects of the function. So now we know that our t is between 0 and pi. We can just use one of the formulas from before because we know it's rotated about the x-axis. We use this formula here, y squared times dx dt, and then integrate in terms of dt. We can substitute our limits, which is pi and 0, which is our ta and tb, and our y squared dx, the same as the formula we said before, and remember to multiply it by pi on the outside. And all we do in the next step is just substitute our y value, which we said was sine 2t from the question. We substitute that into the squared, and for the dx dt, we differentiate the x equation here in terms of t. So we differentiate cos t. And once we do the differentiation, we're going to get pi times the integral of sine squared d2 times t multiplied by, when you differentiate cos, you'll get minus sine. So you get minus sine t here. And from this step onto this step, we'll use double angle formula, which you can find using compound angle formula, or which you will learn in A-level normal maths. And this basically, so the 2 sine 2t expands to 2 cos t sine t over here, and you can substitute that in and square the whole thing and keep the minus sine t multiplied by it. And remember to keep the pi as well. And once you so once you have the squared, you can just take out the squared and expand it out separately. So you have 4, so 2 squared is 4, cos squared is just cos squared, and sine squared is just sine squared. And then you can take out this minus for the next step, so this minus is taken out here. So you just multiply by sine this whole thing, so multiply both of these, and you get 4 cos squared t sine squared t. And I've also left it out, so instead of sine cubed t, which is technically is this, I've left it as sine squared t times sine t. So you can actually leave the sine squared in terms of cos because of this identity here, where cos squared t plus sine squared t is equal to 1. If you rearrange this equation, you're going to get 1 minus cos squared t is equal to actually sine squared t. So you can substitute this sine squared t as this. And now if you expand this out, you're going to get something like this, where you've got still the minus pi on the outside from before, because we've taken out the minus from here. And on the inside, if you expand this out, you do the 4 cos squared t times 1. So you have that, and times sine t. So you have this times 1. So you have this part here. So 4 cos squared t times sine t. And then take away 4 cos squared t times cos squared t. So 4 cos to the power of 4t times the sine t as well. And then because there's a minus in between, you have a minus there. And then because the minus, we can bring it back in. We can just flip this around, these two around, and you have the 4 cos to the power of 4t sine t at the front, because minus and a minus becomes positive, and a minus and a positive becomes negative. So you have minus 4 cos squared t sine t over here. So basically bring this negative. And now all we have to do is integrate this whole thing and remember to multiply it by pi. So all we have to do is integration by substitution, and we'll do this because, as you can see, the cos squared t, because if you can see when we try it out, that if we make our cos t our u, when you do du over dt, you're going to get dt is equal to du over sine minus sine t. And because you have minus sine t, you can easily get rid of that. So let's go through the steps. So you have u is equal to cos t. When you differentiate in terms of t, you'll get minus sine t because cos differentiates into minus sine. If you rearrange this equation, you're going to get du is equal to minus sine t times the dt. So you bring the dt over here, and then you divide by minus sine t on this side over here. And this is equal to dt. So you can substitute your dt as this, what we found here, and your cos t's as our u's. So if we do this, we're going to get, oh, and also you have to do your new limits. So because you're integrating in terms of u instead of t now, your new limits would be, instead of between pi and 0, you would do between cos pi and cos 0, because you substitute your t values inside. And you would do between minus 1 and 1. So your old function becomes pi. Remember, always multiply by pi on the outside because we haven't done anything to that yet. And then you do between, instead of pi and 0, minus 1 and 1. Always keep it the same. So pi relates to, because you substituted pi here, it related to minus 1. So always keep that at the top. And the 0 relates to the 1. So you keep that at the bottom. It doesn't matter if the 1 is larger than the minus 1. So what you would do is now substitute your u, which was cos t, so your cos t now becomes u, and your dt becomes du over sine minus sine t. And as you can see on the function, the sine t just cancels out nicely, so you'll be left with pi times this integral of minus 4 u to the power 4 plus 4u squared du. And this is equal to, so what we do in the next step is just rearrange it to keep it nice and neat. So we'll just put the positive first and the negative after. And once we integrate this, remember all we have to do is just increase the power and divide it by the new power. So u to the power of 2 becomes u to the power of 3, divided by 3, 4 over 3, u to the power of 3, and then 4 becomes 5. So you do minus 4 over 5, so you divide by 5, and u to the power of 5, basically. And then once you do this, you just plug in your old limits like this. So you get minus 1 on one side and 1 on the other, and just take away. Keep multiplying by pi on the outside because we haven't done anything with that yet. And then once you have that, you'll get this, which is minus 4 over 3. You have minus 4 over 3 here, and 5 over 4 and 5 over 4. And if you just collect like terms, you're going to get minus 16 pi over 15. But now you see that this is a negative number but you can't really have a negative volume, can you? So you just do the modulus of this, and your volume would just be 16 pi over 15, and that would be the volume enclosed by this function here of these two parametric equations that we were asked in the question. So now let's move on to the mean value of a function. So this is pretty simple. So if you want to find the mean value of y, so the mean y value of a function between 2 points, b and b, the mean value is just this equation where you do 1 minus the range, so between b and a, so where b and a are x values. So you'll do 1 over the range, the x range, is equal to the multiplied by the integral between that range of the f of x, and that you'll find your y mean function. So let's move on to a question just to apply this quickly. So if you have a mean value of y, so we're asked to find the mean value of y is equal to 20x, and find the mean value between x equals 3 and x equals 18. So all we have to do is just substitute this into the equation, and we're going to get, so our function is 20x, and our range is between 18 to 3. So we'll do 1 over 15 between 18 and 3, and then integrate this. We'll just increase the power, so we get x squared divided by, so 20 divided by 2, which is the new power, 10, and we will do 1 over 15 times that, times the integration here, and just to integrate, we'll do the substitute in the limits, so you substitute your 18 and your 3, and you will get 1 over 15 times this, which would be 18 squared, and 3 squared, which is 9. And once you multiply each one by 10, you will get this, and then you can subtract it and divide it by 15, and you get 3,150 divided by 15, which is equal to 210, which is the mean value of the function of y is equal to 20x between 3 and 18, the values of x, and this will be your mean value for y. As you can see, 210 is not between 3 and 18. So that's the end of the video. Thanks for watching, and I hope this was useful for you.